Well, welcome back, everybody. Hope you had a great and relaxing break, that you maybe got to do something totally different or new. Maybe some of you did some college visiting or were in Zuni, or just hung out at the beach or went and saw some wildflowers. Whatever you did, hope it was great and refreshing and that you're back, ready, recharged. We have 7 weeks to go, so we're in this final push. We're going to launch chapter 5 today, and for those of you who will be taking this class again at some point, maybe in college, your major is going to require it or something like that, chapter 5 would mark the beginning of what would typically in a college class be second semester. So first semester, you would spend the whole time learning all about the derivative and about all of the ways to take a derivative and then what all of a derivative means and how it can be used. And then you would go into your Christmas vacation, and then you'd come back, and when you'd start your next term, your next semester, you would start here at this point. So this is called Calc 2. And Calc 2, I hinted at that, is sort of the opposite of derivatives. So it's learning how to do everything backwards. But we need to lay the groundwork a little bit. We're going to actually refresh ourselves on some geometry first that we need to lay the foundation for what we'll do moving forward. All right, so here we go. We're going to start chapter 5. In this lesson, we're going to talk about area. So we're going to go back to the basics of geometry, area of rectangles and other shapes. And area has specific meaning. If you've taken physics or AP physics with Mr. Edlin, you have talked about what area under a graph maybe means. And so you understand a little bit about that already. We're going to talk about area as it relates to something called accumulation. And so that area has meaning. We're also going to understand that distance is related to the area under a graph. We're going to learn how to estimate a little bit of area. And we're going to learn something specifically to calculus using left and right sums. So that sets the tone for what we're going to do today. We do this because it's completely foundational for everything that we do. And this whole second half of calculus is fundamental to understanding these crucial geometric tools that we've got. So let's start there. We always know that math and science are really closely connected, and we talk about units. You learn about units and unit conversion in your in your science classes, but it relates to what you've been doing in calculus too. So what you maybe would learn as the original function, so say an f of x was measured in meters. When you use derivatives and you take that first derivative, f prime of x, we're introducing time into that. So the units change and it becomes meters per second. And that's a measure of velocity. And then when we take the derivative again and we have f double prime, the units change again. And now we have meters per second squared. So notice that we're dividing by the unit of time. So we start out with meters. And when we divide meters by seconds, then we get meters per second, or meters divided by seconds. Then when we divide again, then we get meters per second squared. So you've been doing that in first semester, or in this, what would be called Calc 1. But the question we're going to ask today is, how do we go the other direction? How do you go from a unit of acceleration and work your way backwards, back to velocity, and then back to position or distance? Is it possible to go the other way? So let's start with a pretty basic question. If an object is in motion for 20 seconds and it has a constant velocity of 10 meters per second, how far does it go? That's the question, right? How far does an object go over the course of 20 seconds with a constant velocity? Well, we use science and the idea of units, and when we look at 10 meters per second, so we're going to write our units like that, and we use multiplication, and we multiply that by 20 seconds, the units reduce each other. So because you have seconds in the denominator and you have seconds in the numerator, those units reduce each other away. And then the straight out multiplication is going to lead you to an answer of 200 with the unit of meters. And so how far, the answer to the question, in those 20 seconds, this object would travel 200 meters. The question, how does it look geometrically? All right, so we always put time on the x-axis. So starting with 0, we'll label that as t. And if we're going to go 20 seconds in time, let's just count by fives. So 5, 10, 15, 20. And then velocity would go on the y-axis. And we can count 2, 4, 6, 8, 10. And we have a constant velocity. And what happens there is with a constant velocity straight out over the course of time, we end up with the shape of a rectangle. And geometrically, that rectangle has dimensions 20 by 10. So we have 20 as its base, we have 10 as its height, and 20 by 10 leads to an area of 200, which is the same as what value that we got using multiplication. So the connection of that is true, that the science, the units of multiplication also match up to what it would look like geometrically. So that's a real basic example. So let's change things a little bit. So what if we keep this object in motion for the same amount of time, 20 seconds, but what if its velocity is not the same? What if its velocity is not 10 as a constant, but is predictable? If the velocity is measured at 10 minus, and I'll need you to correct something on your notes. I left out a fraction here, so I apologize, but there should be a 1/4 there in front of your t. All right, so if you could make that change in your notes, that would be good. All right, so we're talking about, okay, what if I can predict the velocity, but it's not constant, it is changing? What does science tell us? So science would say, okay, 10 minus 1/4 t measured in meters per second as a unit, and then just like last time, we'll multiply by the 20 seconds, and we see that the science tells us that the units reduce, but I don't get a numerical value. I don't get 200 like I did. I do have to distribute this 20, and what I'm going to end up with is 200, but then when I distribute the 20 to the 1/4 t, I'm going to get 5t, and then my units of time, units of measurement is meters. So this isn't a constant value anymore, so I don't actually get an answer. I get an expression, but I don't get a constant value. And what I'm actually looking for is a numerical answer. So would geometry help me instead? Science only got me so far. Let's switch over to math and see how math is always better than science. Just kidding, but the two go hand in hand. All right, so 0 time, and we'll count out again by 5. So 5, 10, 15, 20. There's my 20 units of time, and I'll get my velocity. 2, 4, 6, 8, 10. And I'm going to start with my velocity at 10, but I'm not going to go straight across because it's not constant anymore. My 10 is going down with a slope of down 1/4, down 1/4. And so if I follow that slope down 1/4, I end up with something that looks like this. And that shape is no longer a rectangle. My shape is now, if you remember from geometry, the shape of a trapezoid. And I do still have a base of 20 like I did before. And I have a 10 height on one side, but on the other side I have a smaller height of 5. And so my area has to be the area of a trapezoid. So the area of a trapezoid is not base times height. It's similar to the area of a triangle. It's 1/2 base, and then the two heights added up. So h1 plus h2. So this would be 1/2 of 20, and then 10 plus 15. So we're looking at 10 times 25. So I'm going to get, oops, not 15. You guys probably already said, wait, you made a mistake. 10 plus about 5. I was adding in my head already. So 10 times 15, there we go. So 150, and then the units on that are going to be meters. So this is going to cover, the object will go far less. It's only going to cover 150 meters as opposed to the 200 meters we had the first time. And that's because the velocity is slowing down. It's getting slower as it goes. The velocity started out at 10, but then the velocity got steadily slower. Maybe somebody applied the brakes or whatever, but we just covered less territory. All right, let's see where this takes us. So how about the same object in 20 seconds, but with different velocity values collected? So it's not constant, it's not predictable, they're just various velocity values. What would that look like? So let's forget the science right now. Let's since geometry helped us out last time, let's go right to that again. All right, so we've got our time axis, 0 to 20, and let's see, because the table breaks it up by 4s, I'm going to count like that too. So 4, 8, let's see if I can do this here, 12, 16, okay, so 20 ended up right here. Let's get rid of that other one. Okay, all right, 4, 8, 12, 16, and 20. Okay, and then our velocity. So we have varying velocity values. So we've got 2, 4, 6, 8, 10. So I've got a velocity value of 0, 10. And then 4 dips down to 8. 8 dips down to 7, so about right there. But then 12 goes back up to 9. So down by 2, down by 1, then up by 2, and then 16 goes up again to 12, and then 20 goes up even higher to 16. So not necessarily a predictable pattern because I went down for a little bit, but it wasn't consistent, and then going back up again consistently. So what kind of geometric shape is that? You know, it's not really a consistent geometric shape. It's not a nice rectangle. It's not a nice trapezoid. So we're going to just have to do the best we can. So geometry, can it give us an exact answer? The answer is no, but it can get us pretty close. So what we're going to do is we're going to approach this with something called the rectangular approximation method. And we're going to do our best to estimate. Now, we won't be able to get exact, but we're going to estimate using the idea of drawing various rectangles in and around and under these various dots. Okay, so this is the rectangular approximation method. These stand for the area of different rectangles. And R1 would be the area of the first rectangle. And then R2 is the area of the second, etc. All the way to the final rectangle, whatever rectangle it is. So maybe you're thinking, I didn't see any rectangles. All right, well, let's go back and let's put some rectangles in here. So remember at the beginning when we started at the number 10 and we just went straight across? Let's do that here. Let's go straight across from the number 10 until we get to 4 seconds, and let's go straight down. There's our first rectangle. And that rectangle is a 4 by 10 rectangle. The base is 4, the height is 10. So a 4 by 10 rectangle has an area of 40 as its value. And if we do that from every successive dot, now let's drop down to the value of 8 and let's go straight across and we'll drop down. Okay, that creates another rectangle next to it. That's also a 4, base of 4, but the height this time is 8. So now that's only a 32. Okay, it's a 4 by 8. It has a smaller height. These are where the rectangles come from. You draw the rectangles. It's not going to be perfect, but you're going to superimpose rectangles on there. That is what the rectangle method is. Okay, now I started on the left. I started with the number 10, and that is one method called LRAM. Okay, that's the left rectangular approximation method. It's when you work from left to right. The opposite of that would be RRAM, and that is when you work from right to left. And I usually find that it's easier to color code it on my drawings so that I can see the difference. Okay, so let's try, this is the same example, and so I am just going to draw this a little neater so that we don't have any, we'll be able to color code everything. So I'm going to do my best here across the bottom. So I'm going to do it in black because then my rectangles are beginning to be in different colors. So 4, 8, 12, 16, and 20, and that's my time axis. My velocity values, 2, 4, 6, 8, 10, mark that off, 12, 14, 16, I needed to go up that high. Okay, so let's getting those data points back on here again. I'm going to keep my data points in black. We started at 0, 10, 4, 8. Now if you're working in Notability and you really liked how your first data thing looked and it was good and you didn't make any mistakes, go ahead and copy and paste it. That's fine. I just didn't like mine. Mine didn't turn out quite as nice as I wanted it to, so I'm going to draw it new. Okay, and then 12 here, and 20 goes up to 16. All right, so what I'm going to do is I'm going to pick blue, and I'm going to work left to right. So we already kind of got that started. We did a 10 and then down, and that made a rectangle of 40 because the base was 4 and the height was 10. And then again, working left to right. That one is a base of 4 with a height of 8, so an area of 32. Next one is my smallest rectangle. That only had a height of 7. It still had a base of 4, but it only had a height of 7, so 28. Now I'm going to need to go up a little higher and straight across. Again, I'm working left to right. That had a base of 4 with a height of 9 this time, so that would be 36. And then left to right. That had a base of 4 with a height of 12, so 48. And there's always going to be one left over. So you can see that I have this one because there's nowhere for me to go left to right. If I go from left, there's nothing to attach to. There's no more data points after that. So we do not, there's always going to be one data point over that you don't end up using. Okay, so now I'll be able to come up with an exact geometric value. And I say, okay, this is LRAM. And I'm working left to right, so I'm adding up the areas of the 5 rectangles that I've drawn. So I've got a 40 and a 32 and a 28 and a 36 and a 48. For a grand total of 184. And the units on this, now I can go back to science, and I look at what the units were on the table. Okay, notice that the table's velocity is in feet per second. So if I think about science, I'd be doing feet per second times, and then I'll be doing the time of seconds, and I would see that those would reduce, so that means feet must be the accumulation of the area. So this car, I predict, would go 184 feet. That's using going left to right. I can also make a viable prediction going right to left. So when I go right to left, I start with the dot that I didn't use. Okay, I didn't use the top dot there. Let me get that on there. At 16, that one never got used. So now I'm going to use that one, and I'm going to work right to left. And when I work right to left, I get a bigger rectangle. Okay, I get a rectangle that's taller, still has a base of 4, but it has a height of 64. So it is a taller rectangle covering all this area. And then the next dot, if I work right to left, I also get, this time, a slightly taller rectangle with an area of 48. And then when I work right to left, the next one goes straight across. Okay, that one is a height of 36 because it's a 4x9 rectangle. I'm basically just tracing these dots backwards, right? So I did the 16 first, then I did the 12, then I did the 9. Now I'm ready to do the 7. So the 7 would go across here, and that's going to be my smallest one. That'll have a height of 28. And then the last one I'm going to do is the 8, which again is smaller than the other one. That gives me a 32 area. And once again, I have one value that didn't get used. The one that didn't get used was this 10 that was on the end. So the ends will never get used as you're working your way across. So now I have an RRAM value. And again, I'm working right to left. So I had 64 was the biggest one, or the first one, and then 48, 36, 28, and 32. And this time I get a value of 208 feet. So I have two estimates for this car and how far it traveled. One estimate would predict that the car would go 184 feet in these 20 seconds, and the other would predict it would go 208 feet in these 20 seconds. So I have one that's an underestimate of the value, and I have one that's an overestimate of the value. So to finish it up, we use our average. With the same data, we would use then an average of both the RRAM and the LRAM to find the most reasonable estimate. So remember, we had 184, and then we had 208. We add those together. We multiply by a half or divide by 2 to come up with the most reasonable estimate, because we know that one of them is too small and the other is really too big. And so the most reasonable estimate would be that this car traveled 196 feet during these 20 seconds. So you're going to have some situations where geometry will give you an exact value because either the velocity is constant, which makes a perfect rectangle, or the velocity is predictable using a linear equation, so then you'd come up with a trapezoid, or the velocity values will be more randomized and off of a table, and you would need to use this rectangular approximation method. It helps me to draw it out. I'm a visual person, so I like to make a drawing, a scatter plot for each of my problems, and then draw the rectangles on there. Some of you don't need to do that. Your brains work differently, and so you don't need to do that. But what I do need to see on your homework then is if you're not drawing it, then I need the evidence of your multiplication. Okay, I need you to write out, like I did here, If you're not going to draw it, you're going to at least need to write out your work so that I can see where the answer came from, because all the answers are available online. All the answers are available on the PDF that I posted in Canvas. So I don't really care about the answer as much as I care about you showing me the process of how you got to that answer. What did you add up to arrive at that value? So you don't show me any of the sums, you don't show me any of the additions, I'm not going to give you the points for the effort on the homework. Okay, so just as long as we're come to an understanding for that. Okay, let me know if you have any problems. Feel free to stop by. And I congratulate you on launching into Calc 2. This is exciting, and it's a whole new ball game from here on out. So good luck with this.